Okay, this is the lesson video for section 2.4, rates of change in tangent lines for AP Calculus AB. And what we're going to talk about in this section, even though the title is rates of change in tangent lines, what we're really going to be doing here is transitioning from the idea of a limit into the idea of a derivative. So in this section, they're primarily going to use the description of what we're doing. They're going to call it a tangent slope. But I'm going to use some different terms interchangeably as we go through here. And these all mean the same thing. So when I say tangent slope, or if I say instantaneous rate of change, or if I say the value of the derivative at a point, those are all going to mean the same thing. So when we talk about a tangent slope, keep in mind what a tangent line is from geometry. So that's a line that's going to touch, in our case, it's going to touch our function, but not actually cross through the function at the point of tangency. And so that's really what we're going to be trying to find the value of today. And we'll be able to find those tangent slopes by using what is the definition of a derivative. So primarily today we'll focus on the definition of a derivative at a point. So you can see in this graph down below, we've got a graph where we've got 2 points P and Q. And what we're trying to do here is we're trying to find the tangent slope at the point P. Notice up above, it says the average rate of change of a function over an interval. That's just the slope. When we say average rate of change and slope, those are the same thing. So it's the amount of change over the length of the interval, or the way that you can think of this from algebra is just change in y over change in x. So you can see down below, we've got the slope here of segment PQ. And where that's coming from is that we have 2 points here. The point P would be at x, f of x. So our x value is x, our y value is f of x, and then the point Q would be at x plus h, f of x plus h. So you can see the y value in that case is f of x plus h. So that's where this is coming from now. You can see down below here in this setup, you can see that we've got the change in the function values or the change in the y's over the change in the x's. And that simplifies down. If we simplify that, that simplifies down into this, f of x plus h minus f of x divided by h. Now, notice on the last expression on this page, it says the slope is equal to the limit as h approaches 0. So what they're talking about doing here is taking this point Q, and then we're going to slide it down along this function towards the point P. As that point Q gets closer and closer to the point P, we're going to go from having a secant slope to now we're going to create the tangent slope. So we need Q to get very, very close to the point P so that the slope between those 2 points will then be the tangent slope. So that's what the limit is doing. The limit is going through and it is essentially making those 2 points get infinitely close together. And that actually is what the definition of a derivative is. So next time in class, I'm going to show you an animation of this happening, the point Q approaching the point P, and you'll be able to see the actual lines moving from a secant slope into the tangent slope. Okay, so there's a lot of vocabulary in this section. I already mentioned this, but when we say average rate of change, we're just talking about the slope of a secant line. And when we say a secant line, we're just talking about 2 points on our function that we draw a line between. When we talk about instantaneous rate of change, that's also the slope of the tangent line. That's also the definition of a derivative at a point. So if I say find the value of the derivative at a point, or the instantaneous rate of change, or find the slope of the tangent line, they're all asking for the same thing. Okay, so let's take a look at an example. And what we have here is a graph, excuse me, of y is equal to x squared. So we're looking at the point where x is 2 and y is 4. And what we're going to do is take a second point here where we're at 2 plus h. And then since this is x squared, it would be 2 plus h squared. Okay, so that would be my coordinate. And now what I'm doing here is I'm actually finding the slope between these 2 points. So this was the point 2, 4. Okay, so take a look at what's written out right here. If I want my secant slope, it's just the change in y over the change in x. And you can see that's what's been done, change in y over change in x. Now, if I want to get the tangent slope, what I'm going to do here is I'm going to go from just having that slope equation. And now I'm going to create, essentially, I'm going to create a limit that is going to make the point Q approach the point P. So before I transition this into a limit, what I'm going to do is I'm actually going to take my secant slope and I'm going to simplify this expression down a little bit. So for this expression, if I were to expand this out, what I would have is 4 plus 4h plus h squared minus 4. So that's the numerator expanded out, divided by 2 plus h minus 2 would just be h. And now if I simplify that just a little further, you can see that the 4's are going to cancel each other out. And then also, now that that's gone, I can cancel out an h, and this whole thing just simplifies down into 4 plus h. So my secant slope can be defined as 4 plus h. So now if I want to take it from a secant slope to a tangent slope, I just have to think about, okay, I need the distance between these 2 points to approach 0. And that means that I'm going to take the limit as h approaches 0 of my secant slope, which we said was 4 plus h. Okay, so now when I evaluate that, if I take the limit as h approaches 0 of 4 plus h or h plus 4, you can see we're going to end up with a value of 4. And now I've got my tangent slope. Okay, so if I want to write the equation of the tangent line, remember, for the equation of a line, we just need two things. We need a point and we need a slope. Well, we have the point 2, 4. We have the slope of 4. So it would just be y minus 4 is equal to my slope, which was 4. And that's going to be multiplied by x minus 2. So that's the equation of my tangent line. Now, one thing to keep in mind here when you write the equations of your lines, I want you to kind of get in the habit of leaving them in this point slope form. And the reason that I want you to leave it in the point slope form is because we still have reference to our point of tangency here. And you can see that with this minus 4 and this minus 2, I can see my point of tangency is at the point 2, 4. If you were to take this equation and rewrite it, you could rewrite this as y is equal to 4x, let's see, minus 8 plus 4 minus 4. You could write it like that, but now when I write it this way, I no longer have reference to that point of tangency. So like I said, I would prefer that you write it in this form and get in that habit. That's not only going to help you in this class, but also down the road when you start looking at something we call Taylor series, which is a way that we can model functions, very complicated functions with simple polynomials. We're going to write things in that form. And so really, when I find the equation of a tangent line, this is kind of getting a little beyond the scope of this course, but when I find the equation of a tangent line, what I'm doing is I'm finding what we call a first degree Taylor series. So you're saving yourself a little bit of confusion down the road if you just get in the habit of writing things in the point slope form. Okay, so down below here, I've got a graph just going through some basic vocabulary again. So we just found a tangent line, and you can see the tangent line is tangent to my function f of x. We talked about a secant line. It's just 2 points on my function that are connected. And then the last thing is what we call a normal line. So those of you that have done some physics, you may have seen normal vectors before. The reason that we're going to see normal lines a little bit in this class is because once you get beyond 2D calculus, you really start to get into a lot more vector calculus. And a lot of the applications that we do involve vectors. And in physics, a lot of times with physics, you're going to deal with normal vectors. So to start to get used to that idea, we're going to talk about normal lines just a little bit in this class. So when you're going through your assignment, sometimes they're going to ask you for the equation of the tangent line. Sometimes they're going to ask you for the equation of the normal line. So just realize that the tangent line obviously is tangent to my function at my point of tangency. And then the normal line is just perpendicular to the tangent line. Okay, so when we want to find the slope of the curve, when I say the slope of a curve, that's talking about the instantaneous rate of change. That's talking about the tangent slope. Those are all interchangeable. It's also the derivative at that point. So when you see this form, this is actually the definition of a derivative at a point. Okay, so like I said, your book's not going to present it that way in this section, and you won't see it referred to that way when you go through the homework assignment. But really what we're doing here is we are finding the derivative at a point. Okay, so let's move on to a couple of examples here. So primarily what we're going to do is I'm going to have you guys work through some examples. So I'm going to show you a problem, talk about it a little bit, and then I'll have you pause the video, work through it, and then check your answer. So for this next one, it says find the equation of the tangent line to y is equal to x squared minus 4x at x is equal to 1, and then find the equation of the normal line. Now remember, this is the setup that we're going to use. So we're going to use that setup every time. F of a plus h minus f of a divided by h. In this example, your a value would be 1 because x is equal to 1 is the point where we're trying to evaluate this. Okay, so go ahead and pause the video. Try to work through the equation of the tangent line and the normal line, and then when you're done and you have a solution, unpause the video and check your result. Okay, so here's what you should have ended up with. Notice what I did here. For my first step, I took the limit as h approaches 0, and that's my f of a plus h minus f of a, and that's all divided by h. Now, my f of a plus h is a little bit of a messy expression this time, right? Because we had the equation x squared minus 4x. So when I plug in for x, I plugged in 1 plus h in for x. That's where the 1 plus h squared came from. And then minus 4x is minus 4 times 1 plus h. Okay, so it looks kind of messy, but it's the same thing. And now we saw limits like this before. If I plug in h is 0 into this form right now, I'm going to get 0 over 0. So what I've done is I've expanded out the numerator, and I'm just combining like terms and kind of simplifying it out. And the whole thing simplifies down into this expression, h squared minus 2h divided by h. You can see that now that discontinuity that we had is going to divide out. So we can get rid of the h, and we just have h minus 2. And then when you apply the limit as h approaches 0, you get negative 2. So negative 2 would be my tangent slope, or the value of my derivative at x is equal to 1. And from there, I get the equation of the tangent line. Remember, this is just y minus y1 is equal to my slope times x minus x1. Okay, so fairly simple to do. Sometimes the algebra for this gets a little bit messy, but in terms of the setup, all you're doing is taking the slope between 2 points and then taking the limit as those 2 points get infinitely close together. For the second piece of this, it says find the normal line to the curve. Notice that everything is the same between these two equations. The only difference is this slope is now 1/2 because it's the negative reciprocal of negative 2. So remember, when we have perpendicular slopes, if you multiply them together, you should get negative 1. So if I want to find a perpendicular slope, I just have to take the negative reciprocal of my number. So the negative reciprocal of negative 2 would be 1/2. Okay, so let's take a look at a couple more examples here. And you can see this next one. It says, where does the slope of y is equal to 2 over x equal negative 1/2? And so what you have to do a little bit differently in this case, because they didn't tell us the point where we want to evaluate this. So we can use sort of a general point. We can use the point A. We can just say it's at some value x, but you're still going to plug into that same definition of a derivative or slope, tangent slope formula that we saw a couple of minutes ago. And what you're going to do is take that limit and you're going to set it equal to negative 1/2. So what I mean by that is if we just use like a general x, you could say y prime, or you could say the slope, the tangent slope, or whatever you want to say, but it would be the limit as h approaches 0. And I'm just going to say this is at some arbitrary point x. So that would be f of x plus h minus f of x divided by x plus h minus x. So that would just be divided by h. And now we need to use our function, the 2 over x function, and plug that in. So I'm going to let you pause the video and try to work through that. And then when you unpause it, you can take a look at your solution. Okay, so here is the result that you should have ended up with. And I mentioned this, I think, a couple of classes ago. And the idea is the setup here, the calculus piece of this, is actually only occurring at the very beginning of the problem. The rest of what you're going to do is a lot of algebra. So again, all of that time we spent on prerequisite material, it's because of problems like this. So I showed all the steps here. I'm not going to talk through all these steps, but the main idea is this part of it right here, that's all of my calculus that I do in this problem. The rest of it at that point, except for where I evaluate the limit, but the rest of it at that point is really primarily just algebra. So I've plugged in my x plus h into 2 over x, and I've plugged in my x into 2 over x, and that's where this came from. And now I've got a complex fraction, had to get a common denominator and solve it out. In the end, you can see that we get this as the result of our limit, negative 2 over x squared. So that means that if I want the slope at any point, all I have to know is the x value. So negative 2 over that x value squared would give me the slope, the tangent slope. So in our case, we know we want the slope to be negative 1/2. So I went ahead and set those equal. Negative 1/2 has to equal negative 2 over x squared. I just cross multiplied this and got x squared is 4. So that is going to occur when x is plus or minus 2. And then I just went ahead and found the actual y coordinates as well. Okay, so not that difficult to do from a setup perspective, but like I said, the algebra can get a little bit messy on these. All right, so there's one more example here that I want you to try. This one's more of an application type of problem. And this one, it says the equation for free fall at the surface of Jupiter is given by this position equation. Position is 11.44 t squared meters with t in seconds. Assume the rock is dropped from the top of a 500-meter cliff. Find the speed of the rock at time is 2 seconds. Okay, so remember, if I find from a position function, if I find my instantaneous rate of change, that's going to give me my velocity. And if my velocity is positive, then velocity and speed would be the same thing in that case. So see if you can come up with the setup for that and then solve through to find the speed at time is equal to 2. So go ahead and pause the video. And when you come back, I will show you the solution for this one. Okay, so here is the setup and the solution that I found. My slope, remember, is the limit as h approaches 0 of f of a plus h minus f of a divided by h. I'm using the same setup every time. The difference this time is I am finding essentially the derivative of the position function at time is equal to 2. So what I'm using for a in this case is 2. My function is the 11.44 t squared. So on this first step where I've plugged in this step right here, all I did was plug into our definition of derivative or our tangent slope setup, and I plugged in 2 plus h for the second point in time, and I plugged in 2 for the first point in time because a is equal to 2. And then it's just a matter of expanding this stuff out, canceling out my h, and getting the fact that this is then equivalent to 45.76 meters per second. So it's fairly simple to do. There are really 3 types of problems that you're going to see with this. You're going to see a polynomial type of function like this one. You might see rational functions like this previous one we worked through. And then there's also sometimes when you do these, I'll have you work through them and you'll do some that will involve square roots. And that'll involve that whole process of multiplying by a conjugate like we've done before with limits. So the main idea behind this whole thing is, in this section, you're going to have a lot of these types of questions. The main idea is to keep in mind when they say tangent slope, remember that essentially what we're doing here is we are finding the value of the derivative at a point. So we'll discuss this a little bit more next class, and just email me or message me if you have any questions between now and then.